Why my camera is not working? I don't know what's happening with my camera, but can you hear me? Can you please let me know if you can hear me? We can start early. Please send me a text message, either the TAs or some of the students, to let me know if everything is fine. Of course. Okay, great. So I don't know why the camera is not working though. It's black up, apparently. Let me turn it off and on one final time. USB camera, yeah. Stop video. No. Okay. I'll turn it off. Good morning, everyone. Good afternoon, actually, in China. Today we'll be entering a new chapter in this term in physical properties of polymers. We will be talking extensively about polymer blends and copolymers. And essentially, all this time we have been talking about pure polymers, but today we will be talking about combinations of polymers in the form of polymer blends, okay? And it may be surprising to you, but the majority of polymers that we encounter in our daily life are kind of polymer blends, okay? So they present a large amount of interest, okay? And we need to know how to make these polymers miscible, okay? How we blend them, how we mix them together, and what happens when we mix them together. Polymer blends and copolymers are similar types of polymeric materials, but they are prepared in completely different ways, okay? A polymer blend is essentially a mixture of two polymers that is combined either by melting the two polymer cells and mixing them, or by dissolving them in a solution, okay, in a solvent, and then mixing the two solvents. On the other hand, copolymer requires more delicate chemical procedures, okay? Copolymers require higher degree of attention in terms of the reaction that takes place and the polymerization that we control in order to fabricate precisely different types of copolymers, okay? So we will be talking about different types of polymer blends and advantages of blending. How do we do these blending processes, okay? We will be talking a lot about the thermodynamics and the phase behavior of polymer blends, which are very important for us in order to be able to predict how a polymer blend will behave before even fabricating a polymer blend. How do we compatibilize polymer blends? That is, how do we make two immiscible polymer blends, two polymers that cannot be combined in order to create a continuous phase? How do we make them behave better? Okay, that is compatibilization. Also, how do we detect miscibility? And finally, we will be talking about copolymers, the types, the morphology, the thermodynamics, and a certain family of materials that I already spoke to you very briefly about them. They are thermoplastic elastomers, and they're very interesting. They're mostly kind of copolymers comprising of a soft phase and a hard phase, okay? Where the hard phase can be remelted and recrystallized several times because it is essentially a thermoplastic material, while the soft phase is the elastomeric phase, which gives softness, gives elongation to the material, gives low modulus to the material, and so on. So let's get started with polymer blends, okay? And a polymer blend essentially is a mixture of two or more polymers that have been blended together to create a new material with different physical properties, okay? In general, there are 5 main types of polymer blends. We have, let me write this down. So we have thermoplastic, thermoplastic. We have thermoplastic and rubber blends. We have thermoplastic and thermosetting. And then we have, of course, thermoset with rubber. And finally, polymer with filler blends, where fillers can be either inorganic fillers, such as carbon nanotubes or graphene or silica, that are used in order to improve the properties of a polymer and attribute multifunctionality, such as electrical, thermal conductivity, improvement in mechanical properties. Or it can be more simple situations, such as pigments, dyes, clarifiers, plasticizer. We already talked about these kind of materials, such as the clarifiers or the plasticizers, which can be used to improve the optical properties of a polymer and induce faster nucleation rates and so on. Okay? So polymer blending has generally attracted a lot of attention as an easy and cost-effective method for developing polymeric material that have versatility for commercial applications. Okay? Or, in other words, the properties of the blends can be manipulated according to their use by correct selection of the polymers. Okay? So when we select two different polymers in order to create a blend, essentially what we do is we manipulate their properties. Okay? We manipulate the properties of the ultimate material. As you can realize, the pressure from the market to create new polymers is very high. Okay? So producers of plastics need to provide better and more economic materials. But these materials, even though they should be more economic and be performing better, additionally, they should be cheap again. So there is a very high pressure to the market from the market to the industry. So the industry is finding solutions by creating these 5 types of blends. 1, 2, 3, 4, 5. Okay, so although plastic raw materials are generally more costly in terms of weight than metals, they're more economical in terms of the product cost. And that's why we can have combinations of polymers that can even replace metals, because they are corrosion resistant, they are lightweight, they show good toughness, and they're used for creating a wide range of goods that can be found in different industries. Okay, so the reason for the creation of polymeric blends is mostly reduction in cost, improvement in properties, or even if it's not improvement, we can have tunable properties. Okay, and finally, we have, for the case of immiscible polymers or co-polymers, we have production of unique phase structures at the nanometer level, and we will talk about that tomorrow. On Monday. How do we take advantage of these unique phase structures, these nanostructures at the nanometer level? That takes place, though, only for, use another color, only for immiscible blends or copolymers. Okay, because you realize that in order to create this phase structure, we need to have 2 different phases. Okay, if we have one phase which points towards full, complete miscibility, then we have we cannot produce these phase structures. And a phase structure like that is seen in this picture, in these pictures actually. where we have an immiscible blend of polystyrene and polyethylene glycol. You can see that these materials are not miscible. They cannot be blended in order to create one homogeneous phase, and their immiscibility leads to the production of this spherical structure with diameters in the nanometer level, okay? So, generally, I should point out before going to the first synthetic polymer blend, I should point out that development and commercialization of new polymers usually require many years, and also they are extremely costly, okay? So this is an additional advantage of blends. So because we employ a polymer blending process, which are very cheap to operate, it is also possible to reduce the time to commercialization, okay? I also remember that in order to let's say create those functional blends and so on, more than half of the plastics produced in 2010 were in the form of a blend. Okay, so you can realize that blends are a very important family of polymeric materials. The first synthetic polymer blend was essentially celluloid, which was created by Alexander Parks in UK in 1856 and Hyatt in 1870s in United States, where celluloid was fabricated by blending camphor. Camphor is a very interesting polymer because it can sublimate in atmosphere, okay, in normal atmosphere. So it evaporates if we leave it long enough in atmosphere. And cellulose nitrate, so they blended these two and they created celluloid, and celluloid essentially led the revolution for the production of films, okay, but also led to the creation of these very ugly dolls like these ones, which are a bit creepy as well. And some kids' toys in the past, I highly doubt that any of these, any of the new materials are new toys for kids are made by celluloids. They're usually made from very cheap plastics like polyethylene or polypropylene. Okay? So let's go and talk a bit about the definitions that we will be using throughout these 2 days, essentially, today and Monday, regarding polymer blends. Actually, only today we'll be talking about polymer blends, hopefully. So a polymer blend or a polymer mixture is a member of a class of materials which is essentially analogous to metal alloys, okay? So in a polymer blend, two polymers are blended together to create a new material with different physical properties, okay? In order to have a polymer blend, we need to have a mixture of at least two polymers, or copolymers, it doesn't really matter, in which the ingredient content is above 2 weight %. Okay? So, from ratios higher than 19/2, we have a polymer blend. Polymer ratios between from 19 to 2 ratios, we have polymer blend. So that can be, I don't know, 70/30, can be 10/90, 5/95, it doesn't really matter, okay? So we need the minimum amount of a polymer within the other polymer in order to create a polymer blend is 2 weight %. In order to have a miscible polymer blend, which is homogeneous, absolutely homogeneous to the molecular level, this is associated with a negative value of Gibbs free energy, okay? So the Gibbs free energy needs to be negative. And we also need to have a positive value of the second derivative of the Gibbs free energy. These are the two conditions in order to have a miscible polymer blend. A miscible polymer blend means that we have one phase, a continuous phase for a polymer, okay? There are no two phases at any point of the polymer. It is a perfect polymer blend. And you may find it now very trivial, but the phase behavior can be very complex, okay? We will talk about it later. And many molecular properties influence the physical characteristics of polymer blends, okay? So we said we have two conditions for miscible blends: negative Gibbs free energy, where the Gibbs free energy, you remember, it's given M is the melting minus T delta SM. Okay? Because the entropy is always positive, essentially it's the enthalpy that usually determines whether we have two miscible polymer blends, okay? It plays a major role. It's not only that, but the enthalpy plays a major role towards whether we have a miscible or immiscible polymer blends. For a miscible polymer blend, we have a single phase structure, as I said. We have properties usually averaged between the values of the two polymers, but also depending highly on the ratio. And also we have 1 Tg. Okay, we saw that very briefly, and we will see it again, some examples. And we also very briefly saw about the Florifox equation, which essentially provides the glass transition of a miscible polymer blend, and it is dependent on the weight fractions and the glass transitions of the two polymers. Okay. Now, for the case of an immiscible polymer blends, where the two polymers don't like each other and they don't mix, okay? So we have a phase-separated blend. In this case, the Gibbs free energy is positive, okay? And in this case, we observe 2 Tgs. Forgot to point out the second condition for the miscibility is the second derivative of the Gibbs free energy over the volume fraction with constant temperature and pressure, okay, is positive. Phi is the volume fraction of the polymers. There is one additional type of polymer blends that is called homologous polymer blends. It's not very common, and we will not be talking about that. It's not too interesting, let's say. It's essentially a mixture of the same polymer, but the same polymer displaying different molecular weight distributions, okay? So we have, let's say, low density polyethylene with high density polyethylene, and we mix these two, okay? That is a homologous polymer blend. As you would expect, this is a miscible polymer blend, but doesn't present a significant, let's say, interest towards the blending industry. Yes, I said that the phi is the volume fraction of the polymers, but the volume fraction, you may see it again with this form, F or VF, okay? So all these, if you see this, these are volume fraction. And generally, if we have two polymers, 1 and 2, Phi1 plus Phi2 equals 1, okay? So volume fractions can be, are usually provided in decimals, so 0.2 or 20 weight percent, sorry, volume percent. And Phi2, let's say, is 0.8 or 80 volume percent. Okay, so let's go back to the polymer blends. If we have two chemically different polymer blends, the most common situation is that they will undergo complete phase separation, okay? And they won't be blended. They will form immiscible blend, okay? And in the past, people thought it was almost impossible to achieve miscibility between different polymers. But after intense studies, because of the theoretical and practical importance of polymer blends, nowadays it is recognized that we have polymer-polymer combinations that can be ranging, where the behavior can be ranging from complete miscibility, a homogeneous phase, up to a complete immiscibility, and the creation of these unique structures that we said earlier. So some examples are shown in this picture, this table. For example, polystyrene, PVME is miscible. So polystyrene is generally used in a lot of blends because it presents relatively good properties. So you can see that a lot of blends, these are commercially available blends, have been used for tuning essentially the properties of polystyrene. Let's discuss a bit about the methods of blending. As you can realize, there are a few different types of blending, and the easiest way to blend two polymers is by melting them, okay, increasing the temperature above their melting points, and then combining them within an appropriate equipment, okay? So melt mixing is the first method that we will be talking about, okay? It is the most widely method that is used. And as I said, we increase the temperature of the two polymers or the three polymers, however we want, above their melting points, okay? And then we mix them in an extruder, okay? This is the equipment is called extrusion. The process is called extrusion. And what affects significantly the behavior of melt mixing, okay, and the subsequent behavior of the polymer blends is the temperature of extrusion, okay, the blending duration, and then some obviously parameters such as the ratio between the polymer blends and so on. It is the most widely used method because it is very simple and it's commonly contamination free, okay? Simple and contamination free. Now, we don't have only the option of melting our polymers in order to mix them, but you know that we can dissolve polymers in a solvent and mix the solutions, okay? And that is what is called the solution blending. Let me write down here the process for the solution blending. So, how does solution blending takes place? Firstly, we dissolve our polymers in an appropriate solvent. Okay, so you can realize that the solvent selection is very important because we need to have a certain amount of agreement between solvents. So the two solvents with the two different polymers, when they're blended, they do not phase separate. Okay, so solvent selection is very important. So firstly, we dissolve. Secondly, after we dissolve the polymers in solvents, we mix them together in one vessel and then we stir the solution mixture in order to create a homogeneous solution, okay? So secondly, we stir, or not stir, we mix, let's say. In order to create a homogeneous solution. And finally, we need, of course, to sometimes add compatibilizers or binders if needed. Compatibilizers, as we will see later, are substances that can help make an immiscible polymer blend to immiscible, okay? We will see how these materials do that. And finally, obviously, we need to remove the solvent. This is very important, and complete removal should be ensured. Okay, because any presence of solvent in the final mixture will essentially reduce the ultimate properties of the blend. Okay, so the properties will not be as good or as expected because the solvent essentially within the structure of the polymer will reduce its ultimate properties, making it more brittle, making it less stable thermodynamically, and so on. Latex mixing is another interesting method for blending polymers. Okay, it can be used only for polymer particles that can be suspended in an aqueous medium. Okay, in a water medium. So what is latex? It's a stable suspension of a polymer particles in an aqueous medium. Okay, so we mix these two latex forms and we create this polymer blend, and then we get rid of the aqueous medium, and eventually we end up with an immiscible blend. And finally, we have the fine powder mixing, which is essentially an adaptation of the melt mixing. So essentially, it doesn't have significant differences with melt mixing. The only difference is that before blending the two polymers, we don't use them in a form of polymers, but in a form of pellets. Okay, you know, pellets are these small type of polymer forms, let's say. These are how polymers are essentially bought and produced by industries. and then when we process them, we melt them and so on. Fine powder mixing is essentially we grind those pellets and then melt mix. Okay, so these are main methods that are used for the preparation of polymer blends. This is not something I want you to remember for exams. This is just I get a message. We cannot see you. I know you cannot see me. I tried opening the camera and it's not working. Let me try again. No, it's black for some reason. I don't know. I'll try to fix it in the break, but I don't know why. It's first time this happening. I don't know. Anyway, and interpenetrating polymer networks are not going to be asked for you to remember in the exams. I just put it over there because sometimes people confuse interpenetrating polymer networks with polymer blends, but essentially they're not polymer blends. IPN are two or more polymers in a network form. In this case, let's say, where we have a network of A chains, a network of B chains, and then we end up with a mixture of the two. But this is synthesized or cross-linked in the immediate presence of the other. So we synthesize B in the network of A, okay? So it's completely different preparation method. It's a completely different type of materials. Again, I repeat, I do not ask you to remember anything about that. I just point out that some people confuse these IPNs with polymer blends, but these are not polymer blends, okay? Because they have two main differences from polymer blends or copolymers or graft copolymer or so on. So the main difference is they can swell, but they cannot dissolve, okay, in solvents. And secondly, the flow is suppressed. What does that mean? It means that IPNs show very high viscosity. Okay, we have already spoken about viscosity. It is an indication about how a sample flows, okay, under increased temperature. And now, why do we blend polymers, okay? We said that by blending, we generally reduce the cost. We can reduce the cost, but most importantly, we can improve product performance, okay? So essentially, blending helps us produce materials that have a full set of properties that we want at a low cost. And that is what is called, these days in research, it's called materials by design, okay? So we know what we want to design. We know the ultimate properties of the material that we want to fabricate, okay? And then on the properties that we want, we know which polymers can be combined in order to fabricate a complex structure that can give us the ultimate properties that we want, okay? And that is what is materials by design. A simple example, let's say, is having a very cheap polymer and wanting to use this polymer in an electrically conductive application, let's say. How do we do that? We need to include an electrically conductive filler. Of course, these are expensive, but usually if we are able to design our materials and design our fabrication processes very well, we can produce electrically conductive materials by combining, let's say, carbon nanotubes with a certain very cheap polymer at low amount of carbon nanotubes, then we fabricate a generally low cost, a high performing material. Blending also can improve product performance by extending performance, incorporation of less expensive polymers. Okay. Also very important these days because of general problems with let's say environmental conditions and over littering and the great plastics problem as it is described by media, where plastic essentially are the cause of harm for every, let's say, environmental pollution, which is not the truth. And plastics are not generally that bad in the form that people are presenting them in terms of environmental pollution. But anyway, this is a very large discussion. Blending can provide means to recycle certain kinds of polymers, okay? So by blending, we can improve recyclability, essentially. That is recyclability. And finally, in terms of specific properties, we can improve brittleness, okay? By blending, essentially, let's say, epoxy materials, we know that they are stiff, okay? And they cannot elongate a lot because of very hard crosslinks, a large amount of crosslinks, okay? They behave great in terms of their stiffness and their strength, but they cannot elongate because they have a lot of chemical crosslinks in there that if we break them, we destroy the material. So what we do in order to make epoxies elongate a bit more, we blend them with rubber particles. Okay? So we have a toughened material. So the epoxy stress strain curve generally looks like that, okay? But when we include the rubber in there, we can have a material that looks like that, okay? So it can elongate more. Of course, the presence of rubber reduces a bit the ultimate strength or the modulus, but generally we have higher toughness. Toughness is the area under the stress strain curve, okay? Also, we can have improved solvent and chemical resistance by incorporation of semi-crystalline polymers in an amorphous polymer resin. How do we do that? We do that by increasing the crystallinity. Of course, this depends on, sorry. So when we have an amorphous polymer, we know that crystallinity is almost zero. If we have any, it's because of random structures rather than, let's say, fabrication of crystalline structures in there. So if we blend an amorphous polymer with a semi-crystalline polymer, we improve its solvent and chemical resistance, okay? By creating these crystalline regions within the blend. Also, we have improved flame resistance by incorporation of non-flammable resins into a flammable one, such as styrenics or acrylics with polyvinyl chloride. PVC is polyvinyl chloride. And finally, biodegradability, again, similar to recyclability. We have different types of biodegradable polymers, such as, let's say, polycaprolactone and so on, or polyhydroxyl fumarate and so on. So if we have biodegradable polymers and we mix them with a polymer that does not biodegrade, we create a complex material that is able to biodegrade, and we also have some tunable properties. So we can improve the biodegradability of a certain polymer by blending it with a second one. Okay. Any questions so far? Before we go to thermodynamics of polymer blends? If not, we take a 10-minute break now, because I don't want to enter this part of the course. And after the break, we continue with the thermodynamics of polymer blends and some other aspects such as the phase behavior and so on. Okay, so take a 10-minute break now, a bit earlier than usual, and we'll continue after the break. So let's go back to the thermodynamics of polymer blends that we started talking about. Apologies, I tried fixing the issue with my camera, but I don't know what's happening. I probably need to restart my laptop. You don't lose anything. That's the truth. So, in terms of thermodynamics of polymer blends, we have a certain, we will be discussing a certain number of equations, and apparently the basic thermodynamic relationship that governs the mixing of dissimilar polymers is this equation for the Gibbs free energy. Okay, the Gibbs free energy of mixing equals to the enthalpy of mixing minus the temperature times the entropy of mixing. Okay, and we said that in order to have two polymers that are miscible, we need the Gibbs free energy of mixing to be negative. Now, for the case of low molar mass materials, an increase in temperature usually leads to an increase in delta in this factor. So, increase temperature, increase stuff delta S, M, and that makes delta G, M more negative. Okay? If this makes delta GM more negative, we expect that this leads to better miscibility as the temperature is increased, okay? However, this is not the case for polymers. Okay, as sometimes we found that polymer mixtures usually become less miscible as the temperature is increased. Okay, so that is why we say that the thermodynamics of polymer blends are not 100% accurate, but they give us an indication about why our materials behave the way they do. The most important part that we will be discussing here is this phase behavior of polymer blends, and we will be talking about that extensively in a bit. So, in order to evaluate the thermodynamics of polymer blends, we employ the Higgins theory, which was developed initially for polymer solvent mixtures. Okay. As you can realize, there are some differences between the interactions between polymer and polymer solvent. Okay, we have different intermolecular interactions, hydrogen bonding, and so on between different types of polymers. While polymer and solvent mixtures, we have much more different interactions at the chemical level and no interactions between chains. Okay, so as you would realize, the Higgins theory is not perfect, but again, it's used in order to give us, let's say, an approximation for the thermodynamics of polymer blends. So what does this Higgins lattice model tell us? We have two types of polymer chains. Okay, we have polymer 1, let's say the white one, and polymer 2, the black one. Okay, so we have two types of polymer chains that are considered to be made up of segments that sit on a lattice of identical cells. Okay, polymer 1 occupies a sequence of X1 segments, so we have 1, 2, 3, 4, 5, 6, and so on segments, and polymer 2 occupies a sequence of X2 segments. In this case, the volume fractions are given by these two simple equations, where X1 and X2 are the number of segments for polymer 1 and polymer 2, and Ni1 and N2, Ni1 and Ni2 are the number of molecules for each type of polymer. Okay, so in this case we have two types of molecules for the black one and two types of molecules for the white one, okay? So, in order to develop this theory, essentially, the Flory and Higgins try to derive an expression for the delta G M, delta G of mixing, when we have no enthalpy changes, okay? So there are no changes in rotational, vibrational, and translational entropies of the components upon mixing. And I don't want you to remember these equations because essentially they are derived from essentially the mixing of polymer with solvent. Only thing I want to point out towards you is that after having zero enthalpy, okay, in this equation, we have that the Gibbs free energy of the mixing is mainly affected by the combinatorial entropy of our mixture, okay? The contact, the delta GM contact is given by this equation. There's no point in going through this because it is derived essentially from polymer solvent mixtures, which is not the same with polymer mixtures, but anyway, people use it for polymer mixtures. Delta GM contact is given by these parameters, which we all know them, okay? This is a constant, this is the temperature, this is X1, we said it is the number of segments. N1, we know that it is the number of molecules for polymer 1. Phi2 is the volume fraction, and X, that he actually is the Flory-Higgins interaction parameter, okay? That is an important parameter, okay? Because it can provide information regarding miscibility. So the Flory-Higgins interaction parameter is a criterion okay? And because the Flory-Higgins interaction parameter is given by this equation, where alpha and beta are constants for each polymer, okay? When we increase the temperature and we substitute here, we substitute he to this delta G contact, we see that the delta G M becomes less negative, okay? So we have decreased miscibility, and that's why we said earlier that when we increase the temperature, we don't have always increased miscibility for mixtures. We actually have decreased miscibility. So the combinatorial entropy of the blends is given by this equation. Again, I tell you, I don't want you to remember that. This is always negative, okay? Because phi1 and phi2 are less than 1, and we know that the logarithm of a fraction is a negative value, okay? Only thing I want you to remember, though, is the Gibbs free energy, the Flory-Higgins equation for the Gibbs free energy of mixing for a polymer blend, okay? I want you to remember this equation. And in this equation, we have three terms, as you can see. We have the first two terms, which are the combinatorial entropy or mixing, 1 and 2, and finally we have the enthalpy term. Okay? Obviously, because in polymer blends, N1 and N2 are very small, The thermodynamics of mixing are dominated by the enthalpy, as we said in the beginning of the class, okay? So the Gibbs free energy of mixing is mostly affected by the enthalpic term because N1 and E2 usually are very small in polymer-polymer mixtures. I want you to remember this equation, okay? All the others, because I don't present you the way that we derive this. This is very complex even for your expertise and your let's say ease of using mathematics. So we just present you, and all I want you to know is this Florifox equation, which is very simple, of course. Now, let's go to something very interesting. Let's go to the phase behavior of polymer blends. And essentially, by creating these phase diagrams, we are able to predict at which point and which temperature and which composition we will have miscibility between a polymer blend or immiscibility. So we have a two-phase region and one-phase region. The phase diagram consists of temperature versus composition. But let me create a new node and let's go through the phase diagram, the phase behavior together. Okay, so we have the phase behavior. In order to study the phase behavior, it's better if we divide the Florifox equation in order to have molar quantities. So we need to divide by x1 E1 and x2 N2. Okay, so if we divide Florifox equation by x1 E1 and we already said that N1 and N2 are the numbers of moles of the two polymers that are present in the blend, and X1 and X2 are numbers of segments of each type of polymer, okay? So in this case, the Gibbs free energy of mixing per mole of segments is given by this equation. Let me write down the equation and I'll get back to you. I saw someone posted something. So yes, in this case, because we have a negative value of the logarithms of phi1 and phi2, then we have these parameters, the combinatorial entropy of mixing that is very small. D1 is usually small, I agree, but this case, this parameter, the enthalpic term, is not very small because we do not have any negative values. Phi1 and phi2 are fractions, okay? And we said already that these are negative, okay? So because these two parameter terms 1 and 2 are negative, and N1 and N2 are very small, then we're talking about values in the order close to 0 or negative, okay? So let's fabricate now our phase diagram, okay? The phase diagram for polymer blends looks like that. We have on the x-axis the composition, let's say Phi1, and then of one type of polymer, and on the y-axis we have the temperature. There are two regions, okay? We have a single region where we have a single phase, and we have different regions where we have two-phase regions, okay? The curves that separate the single phase from the two-phase regions are called binodals, okay? This is a binodal, and this is a binodal. As I said, everything here between these binodals, come on. So in here we have single when we move at temperatures in this region and compositions in this region, we have a single phase region. However, in the case for a two-phase region, we have a separation within this two-phase region. Okay, where there is a metastable region, okay? This region here is metastable. These red regions are metastable. So they show a behavior between a two-phase and a single-phase region, okay? So this is metastable, this is metastable. The curves that separate the metastable region from the two-phase region are called spinodals. Okay, let me paint this one as well. Here we have the two-phase region, where essentially in two-phase region, what do we say? The blends are immiscible, okay? There is not a continuous mixture in this case, but there is the presence of both polymers clearly within the blend. So, so we create these immiscible structures in our blend, okay? So I said that the metastable region is divided by the two-phase region with the spinodal curves, and the single-phase region is divided by the metastable region or the two-phase region with the binodal curves, okay? This is the lower critical point. And this is the upper. The most interesting parts are, as I said, that we have single phase region between binodals. Secondly, we have in the two phase regions, we have immiscibility. And three, for the metastable region, we can find this between binodal and spinodal. Okay? And there is this phenomenon that is called spinodal decomposition, okay? Spinodal. We have spinodal decomposition when the system moves from a single phase to two phase spontaneously, okay? So it goes instantaneously from single phase to two phase mode, let's say. As you can realize from this graph, what are the results in order to have phase separation? We will have to have a change in composition or a change in temperature, okay? So phase separation takes place if we have change composition or change in temperature. In order to do so, we need to cross binodal or spinodals, okay? Also, we said that in order to have the condition to have a phase separation is that the second derivative of the Gibbs free energy of mixing over volume is 0, okay? Sorry. Gibbs free energy of mixing over volume is 0. So, if we take the second derivative of the Gibbs free energy of mixing equal to 0, that is the condition. So we end up with an equation that looks like that. Okay, but we already know that he is given by alpha plus beta over temperature. So if we know these two, we can construct a theoretical spinodal curve, and that is how we are able to predict the phase behavior of a polymer blend. So a theoretical okay, and also in order to know the critical composition, in order to pass from a two-phase region to a single-phase region, the critical composition are these ones, okay? In order to find that, we need to take the third derivative of the Gibbs free energy to be 0. So in this case, for the critical be 0. If we substitute to the Higgins equation and we take the third derivative of the Gibbs free energy, we end up with this equation for the critical composition, 1 over and also we can calculate the Florifox interaction parameter given by this is very badly written, E1 1 over 2, E2 1 over 2. That's squared. Okay. So that is how the phase diagrams are essentially fabricated, and a wealth of information, a lot of information extracted from a phase diagram. Now, in order to sharpen a bit your maths, we can go together these derivatives, okay, for the Gibbs free energy of mixing, in order to have phase separation or not. In order to do that, firstly, we need to remember that the derivative of a logarithm is 1 over x, okay? And the derivative of two functions Okay, so if we now go to take the second derivative of the Gibbs free energy over the volume fraction to be 0, we need to start from firstly deriving the Gibbs free energy of mixing over volume, and essentially what we do is take the derivative of the volume over the Florifox equation. Sorry, but should have done this bigger. And then 1 minus f1 plus x. And that gives us this equation, which we need to derive again in order to take the second derivative. I will provide you this. If you don't want to keep notes of this, I will provide you this after we finish this section. And after we finish today, I'll also provide you with the notes from the glass transition, which I haven't done yet. I'll do that after we finish. Okay, so this is equation 1. Now we need to derive again equation 1 in order to get the second derivative to define the spinodal point, okay? So second derivative, I'll only do this for the spinodal point. I won't be doing it for the critical temperature. You can do it yourself if you want for the critical temperature, and let me know how it goes. The F1. Sorry, minus. So that gives us 0 plus 1 over x1 f1 plus 1 over x2 1 minus f1 minus 0 plus 0 minus 2x. And that should be 0, okay? And eventually the equation that gives us the defining spinodal points, the spinodal curve, is 1 over x1 phi 1 plus 1 over x2 1 minus phi 1 minus 2x. Okay, that is, if we plot this, we define the spinodal points. Okay. Also, if you want, you can do it yourself. As I said, for the critical temperature, we said that the critical temperature is equal to a third derivative of the Gibbs free energy to be 0. Okay. Now, let's go back to the notes. Come on. What is it? Yes, we talk about all these when phase separation takes place. When do we cross? The metastable regions or the two-phase region to single-phase region? Okay. Now, how do we detect miscibility? Okay, we know that we mix two polymers, and how do we detect miscibility? Well, the simplest case of detecting miscibility is by evaluation of the glass transition temperature. And how did we say that we mainly look upon the glass transition temperature? We use differential scanning calorimetry, or the other technique that we said is DMTA or DMA. Okay? This is from DMA, of course. We said if we have two completely immiscible blends, then we have two TGs. And the TGs are, of course, dependent on the glass transitions of the polymers that are blended. For completely miscible polymers, we have this simple but very useful equation. I think it's called Fox equation, Florifox, if I'm not mistaken. Okay, where the inverse of the glass transition of a blend is equal to the weight of the first polymer over the glass transition of the first polymer, and plus the weight of the second polymer and the glass transition of the second polymer. Now, there is a case where we can have what is called partial miscibility, okay? So partial miscibility is, of course, a certain category of immiscibility. So we're talking about still immiscible blends, okay? In this case, we can see two glass transition temperatures, but in this case, we will be for the phase that is rich in component 1, and the other will be for the phase that is rich in component 2, okay? These two glass transition temperatures will be between those of the two component polymers, and of course, they will depend on the ratio depending okay. If we have partially miscible materials, let's say we create again these structures of a polymer within a second one. So if we have polymer 1 is the sick. If we have polymer 1, the yellow polymer in here, and the white one is this, let's say, these dots here are the second polymer, polymer 1. For a partially miscible material, we have good interfacial adhesion between the polymers, okay? So the blend behaves like a good composite blend. So in this case, we have good interfacial. And how do we ensure that the interfacial adhesion is good? This interface here, okay, is strong, okay? It is not weak, and it does not have any holes or anything. So it behaves good in terms of its properties, but still we have phase separation. So that's why we say that they are only partially miscible, because they have good interface between the two materials. So partially miscible are kind of immiscible materials that have good adhesion between the interface between the two polymers, okay? So we don't have one phase, we have two phases where the interfacial adhesion is good. Okay, that's all I want you to remember. In this case, as I said, we have two glass transitions. As you can see here, there is one glass transition here. That is because of the A polymer, and we have a second glass transition here because of the B polymer, okay? And where these glass transitions A and B are found, TG1A and TG2B are found, depends on composition. Okay? Now, as we said, the majority of polymer-polymer mixtures don't like each other, okay? Unless they are from the same family of polymers, okay? If they are, let's say, relatives, such as some thermoplastics or some different types of let's say, polyethylenes, where we have same type of polymer but with different molecular weight distributions. So in order to ensure that we have good dispersion of one phase within the other, and we have a good behavior in those immiscible blends, we use this process that is called compatibilization, okay? And what does compatibilization does? essentially it leads to a good interface between the two phases, okay? We still have two phases. We cannot transform any miscible blend to miscible through compatibilization. However, we can make their properties be much better than they should be, okay? So compatibilization leads okay? How do we do that? Firstly, first method is use in situ polymerization. So in this case, covalent bonding is produced between the two polymers, and that leads to not a blend in this case, but it leads to the fabrication of graft or block copolymers that stabilize the interface, okay? So we create covalent bonding, and in this case, I will explain a bit more because I have some schematic here. So addition of a block copolymer is very similar to in situ polymer. Bondings are very strong bonds between the two phases. Okay? Now, another method is the addition of a third polymer, a ternary polymeric component, a polymer that has good interfacial adhesion with both phases and in concentrates in the interfacial region. I point out again that the key to improve compatibilization is fabricating a good interface, okay? I showed you already what a good interface is. A good interface is this region between separating the two phases here. Okay, this region separating the two phases here being very strong and being essentially continuous, not producing holes or gaps that can act as failure points during testing. Okay, so in this case, when we add a third polymeric component in there, a polymer that has good interfacial adhesion with both phases and concentrates in the interfacial regions, what we do is achieve good dispersion and we also leads to efficient stress transfer. Okay. Reactive compatibilization is another technique where a third polymer, which is miscible with one phase and capable of reacting with the other, leads to the formation of a graft copolymer that will bridge the interface. Okay, the formation of a graft copolymer is always a good thing in trying to do compatibilization because, again, we have a material, a polymer that bridges the interface between the two, okay? And finally, we have reactive extrusion, where essentially chemical reactions take place during the blending process, okay? So we melt our polymers, and at elevated temperatures within the extruder, we have some chemical reactions that enhance the interface between the two phases, okay? Again, it leads to the formation of graft copolymers, as you can see, and leads to an efficient interface between two phases. We will stop here. I'll finalize this part of Polymer Blends tomorrow, where we, not tomorrow, sorry, on Monday. We will briefly talk about block copolymer, how block copolymers can be used to compatibilize polymer blends, and then we will move on to copolymers, which also show a lot of interest, but they're a bit more delicate in order to fabricate them and in order to evaluate their behavior. Okay, so it was good seeing you today. Thank you very much for your attention. Have a good weekend, and I will see you back on Monday. Okay. Enjoy your weekend. I hope the weather is fine in Xi'an. The weather here is a bit rainy today, so I hope you'll be able to take some time. Bye now. Good to see you guys.